Thank you. So to start things off, I just don't want to go off to any assumptions too quickly. I'm going to talk a little bit about what Keyman is, kind of where we're coming from with doing this. So a little bit of background that just kind of informs some of the decisions that were made in the design that we have. I'm going to talk about some of what it is, what it can do, and then of course the big question is how do you get communities to be able to actually piece together their own predictive text solution using the engine that we've made. So a little bit of stuff up front in case you're wondering about, hey, what are the rights, what are the limitations here? Our solution is 100% open sourced. We use the MIT license. It's long-standing, very permissive, pretty free. It's done in TypeScript. So admittedly, there will be some limitations in regards to being able to integrate this into desktop platforms. We do hope to be able to address that in time. Right now, we're focused on the mobile device market in this regard, since it's a lot more useful there, considering there's a little bit less accuracy when you have fat fingering being a little more possible than standard home row typing. We've had this in place since late 2019, so for about 2 years now. Despite being only 2 years old, we already have lexical models that have been submitted for over 20 languages. At last count, we have 24, I believe it was, currently in our repo, and we initially only developed 2. Well, actually, we had a partnership with the National Research Council of Canada who submitted even those 2 as part of the the bootstrapping process. It's hard to verify your solution if you don't have anything to test it with, right? And there's some distinctly non-Roman script languages here. We have Amharic on the right-hand side, and a Nepalese language, Nuwa, that these communities have actually submitted predictive text solutions that are usable here. I can't tell you what the suggestions are, but I believe that they are completely reasonable, and I have looked at them in the past. It takes a good detailed look, so we're not going to spend the time on those screenshots right now. So we accept and distribute any models that are MIT licensed. If a language community is fine giving that licensing, we will take those models into our repository so we can do maintenance on it. It's kind of hard to do maintenance if you don't have the right to do so. So that's the reason we have that restriction for anything we distribute. But users can decide to develop it, put their own licensing, and distribute through other channels should they so desire. We just can't legally maintain that on their behalf, but we don't restrict to this licensing in general. It's just it is a little harder to get it passed around. Some language communities do prefer to stay closed source to more tightly manage their data, and that's fine. We will allow that. We have no desire to police or own any languages data. It's just we're making it possible to get it on their devices more easily. Now, in terms of Keyman and what it is, a little history. It is a software keyboard app that's available on all major platforms: Windows, Mac OS, Linux, iOS, Android, and actually even in most of your major web browsers. We constantly test against Safari, Chrome, and Firefox. We used to do IE, but fortunately that is now outdated enough we can finally lay that fellow to rest. Very glad about that. Now it's Android that's the issue, some of its older browsers. This app will remap your hardware keyboard, so with a US English keyboard you can type whatever keyboard you want to, so long as it's in the system. We provide an on-screen keyboard on demand, or actually by default on your mobile devices because of how touch devices work. We integrate into the operating system whenever you activate it. The first version was released in 1993, originally designed by a 16-year-old by the name of Mark Durden, who was looking to help his father type Lao. Lo and behold, it became his life's work, and he is still in the project today. He just couldn't join us for this presentation. And we have nearly 700 distinct keyboard layouts that serve over 2,100 languages. And this continues to grow over time as people learn about Keyman, experiment, try things out, and work with it. Our keyboards have been available a lot longer than predictive text, so there's naturally a little disparity in our offerings there. Now, in terms of why I want to talk about keyboards when this is a predictive text talk, keep in mind that predictive text, especially on mobile devices, often does consider your underlying keyboard layout. Whenever you hit a key, what keys are beside that? What might you have intended to type? For simple keyboards, it can be pretty straightforward how you adjust for that. But as has been noted in some other talks, there can actually be a lot going on under the hood with some keyboards where you can have some very complicated things happening. I don't have it in this slide deck, but I can mention a very interesting Keyman example where you have some complicated visual aliasing that can happen because two vowels, when put together, look like a third very distinct separate vowel. And then there's some other features of the language to where you can have things with an appearance that the computer doesn't understand underneath because the way we see it is not how it's actually encoded. If you want a keyboard that can correct for that, that starts complicating the issue when you start thinking, now how do I do predictive text when I have this variable encoding that may need to be altered as we go, or when diacritics are added? How do we make sure that no matter what keyboard is needed for a language, no matter what complex operations it has to do with the keystrokes, how do we make sure we still offer good predictions? If we want to make this available for communities, especially long-tail communities, how do we make sure that these issues stay out of the way of any predictive text data and design that these communities would have to interact with? As a result, we have put in considerable effort to actually keep the predictive text engine in a manner that can connect to keyboard layout data, but does not require the community's design to consider it whatsoever. So there's a fair bit of runtime operations that happen, and it helps to understand how keyboards can operate to understand how some of the features are going to be pretty useful. So while Keyman's existing paradigm for handling keystrokes and doing complex operations behind the hood does differ from how LDML plans to specify that with the upcoming standard for CLDR, that standard still accomplishes the same sort of things, and it will be able to adapt to work with keyboards of that manner as well. But the rules accomplish the same end goals even now. So just for some simple examples of some basic things, and then some slightly less basic things that can happen with keystrokes. Your starting point, very simple, plain keystroke remapping operations. We can map E to a E-like vowel in Keyman, to a A vowel, and then O to the corresponding Keyman vowel as well. There are a few E variants, and I always have like 3 that look pretty similar there, and it's always difficulty without context to remember which one is which. So apologies there. So note, the first example and the second set, those 2 vowels are standalone distinct vowels. When you put them together, they look just like the O vowel, but they are distinct. But should we actually represent them as separate if the user is typing them together like this to compose that O? What they probably want is for us to take those 2 and piece them together into that O vowel so that we have consistent encoding on what is meant to be that vowel. So the trigger would be, here's the existing context on the left, then plus, when this keystroke occurs, transform context plus keystroke into the correct output. Even that is relatively straightforward, but sometimes you can get some interesting complications that arise. Same language, just a little more detail. There's a canonical character ordering, and there's some fun just graphing setup where you have clusters. So all of that is a single cluster representing 1 syllable. The word is knyong. Me, or I. So you've got the base character, you've got markers that transform base consonants into their subconsonant or conjunct forms. If you were in Norbert Lindbergh's talk the other day, it's the same idea. Jung is the word for foot. They're actually kind of practical with their technical terms in Keyman. It's literally the foot form of the consonant because it goes below the base. Then the actual consonant being used underneath, and then vowels as they apply. So some example of mildly complicated things you might need to do. We could say, if you have a vowel, and then try to add a subconsonant, the ordering says the subconsonant comes before the vowel. So we reorder that. So we move the subconsonant marker that was in position 2, we output it at position 1. Likewise, we take position 3 and move it into position 2, and then position 1 into position 3. For the second example, this one is not Keyman, but this is a little straightforward to happen, so I'm cheating using a different script here. But if you output E and then an accent mark, you might mean for there to be composition, piece them together. So note also the any vowel and matching. The exact terms used there are a little bit different. Users can define character sets. So you can define vowel as anything that functions as a vowel, and then a similar character array to fill in the vowel with rav mark here. And you can do array-based rule application, so you don't have to specify literally every vowel version of the rule separately. It's somewhat expressive. And then finally, if we have subconsonantal marker, and then we don't give it a consonant, we use a vowel. Well, we kind of canceled that operation. We should probably just drop that subconsonant marker. It's not intended. Just get rid of it. So we will erase that because vowels just cannot fill that role. So these are some keyword rules that can help clean up user input and make sure that it's more consistent. And possibly also provide a bit of error feedback if needed. Now consider, that's how a keyword might operate and help clean up a language. Just behind the hood, no suggestions needed. Now what happens if we also wish to make predictions or corrections on what the user is actually meaning to type? We want to have a low bar to entry for language communities. The less that technology gets in their way when defining how to make good suggestions, the better. So we want the design to be language independent and generalized. Work with any keyboard of the language. As long as it's for that language, we want to be able to make good suggestions for it that are still as well informed as possible. There will be some approximations taken under the hood. We do want to keep things decently optimized and respect the user's device and battery. Models and keyboards can be authored in our developer program. It will work with all keyboards that target the same BCP47 tag as, so keyboard and model, if it's shared, we can link them. So the same predictive text solution can actually work no matter which keyboard as long as it matches the proper tag. Sorry, I forgot exactly which order these slides were in. So in terms of basic predictive text stuff, if you're familiar with the field, you're probably at least somewhat familiar with the idea of the edit distance. How you, basically your old classical spell checking. When typing, there's 3 common mistake types that can occur, technically a 4th if you want to add the Demoreau-Levenstein aspect. You have where you accidentally add an extra character, you accidentally forget a character, or you bat-fingered and hit the wrong character. When you add in the 4th, perhaps you're typing with 2 hands and one finger accidentally lands before the other one. You have an out of order scenario. So each mark off in this direction gives you some notion of how far what you typed is from what you meant to type. And so you can use that distance to say how close is what was typed to actual words of the language. Oh, okay, cool, put it together. Consider how that might interact with corrective keyboard rules. This is where things start to get a little funky and is why things aren't necessarily as straightforward without good care. So here in green, I've marked the key that the user in this scenario has actually pressed. Also, note the current context. We have consonant plus vowel, and we're starting a subconsonant. And to keep it simple, there are two different rule types that could possibly apply in this scenario. We're starting a subconsonant after a vowel. As mentioned earlier, subconsonants come before the vowel. So if this is actually a subconsonant, we need to move it up. But if the user actually meant to type a vowel, we should just drop the subconsonant marker and all is probably fine. Well, if you know Keyman, not actually fine because you only ever have one vowel in a syllable, so there really shouldn't be two. But as noted, sometimes you have that vowel composition effect where you have two different vowels that should be one, and that's another layer that should be triggered. We're not going to look at the full ramifications. Even this is complex enough to sit here and digest in a moment. So if we type the character that was directly typed, and we set that as a true keystroke, then we apply the consonant reorder rule and we move it up. Of course, we could have fat-fingered with the neighboring key, in which case, okay, the key just to the right is also a consonant, so we can apply the same rule. So that's a pretty similar mistake, even in the raw text output. But if we actually happen to hit near the top of the key, because we actually meant to hit the vowel above it, an entirely different keyboard rule occurs. So here we drop the subconsonant marker, we leave the original vowel in its position, and we output a vowel. Now, if we're going by just plain raw text-based edit distance, the first two are a distance of 1 from each other. The only thing that differs is that subconsonant. But if we do the vowel one, the vowel version is 3 edit distance away in terms of the raw text. Because we're not reordering things, we drop this subconsonant. The original vowel stays where it is, we didn't move it. And then we have this different character too. Now, what do you think a user thinks about how similar or different these results are? When you're typing and making possible fat fingers, is the last one actually any more distant than the other two? How do we make sure that we accommodate that? We posit, as many of you might, just thinking about it for a second, that what end users expect the edit distance to be is how far their keystroke sequence is from what they intended to type. If there are transformations under the hood, to them that should be invisible. It should just work. It should be just as simple as if it were, just a simple text output. And of course, there should be some notion of fat finger distance, how close the replacement key is to what you actually pressed. If I press the bottom of the key in green, I would not expect the suggestion with the vowel above it. Not as strongly anyway. I might have gotten badly misaligned, but probably not. I should probably more strongly consider the characters below instead. So there's also a bit of probabilistic distance that you can start factoring in. Now I have a couple of slides in case anybody is technically inclined, wants to know a bit more detail about what's going on. the solution that we landed on that helps make the magic happen, to where we actually do consider those keyboard rules and make sure that the distance is what the user would expect it to be as well as possible, is by actually applying the edit distance again. We note that there's the distance in what was the text output by the keystroke sequence I'm currently considering, and how far is that from the actual suggestion. So how different is it from what the user actually typed, or how much more or less likely? And then how likely is the actual word I'm going to suggest? Then of course there's considering, okay, which keystroke sequences do we consider? And it turns out the best way to proceed with that is to actually kind of reinterpret the edit distance again. We've got probabilities on how likely my fat fingers are, so just use that as the notion of, oh, I'm this far off from having typed that key instead. It's this much less likely. And sometimes you might need to actually consider if a key is outright dropped or accidentally was added. Have some notion of how likely that is. Substitution is the easiest one in this case. So it's not uniform at this point, unlike the classical Levenstein edit distance, but the same principles do apply. So we find the closest viable keystroke level corrections. Like something could look really likely, but if I type 3 consonants in a row in standard English, that's not likely to give me any good suggestions unless it's the STR prefix. Or maybe CHR. There's a few limited ones where that can work. Maybe if it were Welsh, there'd be a lot, but in English, it's not likely to be quite as viable. And so we can prune some of those possible paths early. But as we have likely suggestions that are also match well with likely keystroke sequences, we can continue down that rabbit trail, which is probably pretty productive. But when it no longer looks good, prune it. And the most technical line here is that what we end up doing is dynamically generating a search graph. As we go along, okay, these are my current most likely keystroke sequences that give good suggestions. Let's expand the graph in that direction. Let's keep going. But once, as it goes, then sometimes you need to look at other paths too. These notions of edit distance together give us a heuristic that we can use with A*. And note, heuristic, we are not able to guarantee admissibility at this time, if you're familiar with what that means. If you're not, it means we can't guarantee that we're going to give you the absolute best suggestions, but we're making our best guess. If we could go admissible, we could actually make that guarantee. That's the difference here. But enough technical things. Let's just get back to what the language community is going to more directly think about and care about. We do need to make the assumption for now that we actually know how to word break your language. For most languages, we have spaces. Nice, easy, simple. But there are some of those Southeast Asian languages, like Khmer, that don't do that. So it's actually pretty tricky at this point. As good word breaking solutions become available, we can use that and work. But for things like Khmer and Thai, typically the word breaking solution actually is dictionary based. We'd actually love to be able to, okay, we have a dictionary for the predictive text, let's just use that. Believe me, I agree with you, we just have to have the time and resources to invest into making that word breaker. We just haven't gotten to do so yet. So it is a current limitation. Our apologies. Outside of this one major assumption, we require minimal language-specific knowledge. You can give us a little information to better tailor suggestions, like when typing a sentence. Many people like the double tap space to output a period. Well, some languages use something that's not a standard period. Okay, what should the sentence end punctuation be? Tell us, and we can output that. Otherwise, you might get stuck with the period instead. Also, whenever you go to revert a suggestion, you're probably used to seeing quotes on it in English. What are the appropriate language quotes for the language being modeled? That we can't just magically know ahead of time. Just give us that, and we'll go with it. The most we can currently support at this time are weighted wordless models. Even if all you have is just a raw dictionary, we can work with that. Of course, we can give you better suggestions if we know which words are actually more likely. This is, of course, the minimal baseline. It's kind of hard to be able to give suggestions if you don't actually know what words are even possible in the language. This is the most basic place to start and requires, of course, pretty much the least technical knowledge. Dictionaries aren't that hard to come by for English. They can be for many languages, but often whenever a linguist is working with a new language community, you're going to solicit a word list anyway as part of the process of analyzing the language. So if you've gotten to the point you actually care about predictive text, you probably have some sort of word list somewhere. And if you can have frequency data with that, even better. But we're not even going to require that. In time, we do hope to be able to do more complicated models. It's just a matter of resourcing. Right now, Keyman is developed by 6-7 developers. We're all, it's open source, we're nonprofit. We can't exactly go out and grab tons of new people and fund them to make this thing go a little quicker. So it's still in development, but even still, we've got 20-odd language communities that have actually started doing predictive text using this engine. Also, one benefit is that wordless models are pretty easy to compile for efficiency. There's some nice data structures that can help us stay pretty conformant if we can have that guarantee. Now, to do the actual implementation, what do you need? Here we can have an initial little bitty word list. This is just a subset. We actually do have a lot more words for this language and an active model for it. If you're not familiar with Sanchatan, it is a language spoken by one of the first peoples in Canada. This was actually one of our first 2 models. This was contributed by that National Research Council of Canada. So you can specify this data in one or more. If you want to just have it be composited from multiple files, cool, go for it. Just have them specified in tab-separated value files. If you're familiar with comma-separated, literally just do tabs, not commas. The most basic text-based spreadsheet you could ask for. Since it's such a basic data format, Google Sheets, Microsoft Excel, they can output to this. And many other tools, it's very, very easy for another tool to adopt this. So we've made sure even on this front, the technical barrier to entry is really low. There are also some linguistic-oriented tools that aren't exactly spreadsheet applications, and those can even output these sorts of files for you. And also, those linguistic applications might even have some good frequency data if you've fed it corpuses. They can do that analysis for you behind the scenes. Awesome. This count field is used to determine frequencies, thus how likely the word is. You can just have it as plain counts, and we'll sum it all up on your behalf. That's easy for computers, so no worries there. The compiler will attempt to perform deduplication on your behalf. So you don't have to go in and clean up things if you did accidentally put the same word in different files. Files should be encoded, pretty standard, use UTF-8. And please make sure your normalization is consistent. Deduplication can get a little tricky if one is in FC, the other is in FD. That can be a little awkward. We do have a validation step that'll kind of warn you if there's a potential issue there. We do provide some default word breakers. We have one that it was coded to the Unicode standard default word breaker as of a few years ago. If there's updates to be made, we probably should go in and fix that up. But there's a pretty decent one available for you. It's obviously not appropriate for all languages, but it'll cover a good many. And we also even allow you to specify a custom word breaker if needed. That is totally configurable if you know a little bit of JavaScript or TypeScript. Let's see. Okay. So There are still a few issues left to talk about with predictive text in terms of making sure that it works in a way that feels natural. Suppose our language has casing. Which of these two options is a better suggestion for capital T HD? Which one is more likely to be in our word list? Is it the same one? Probably not. So how do we make sure that our suggestion engine actually can accommodate this? Another one, fiancé. To me, it just looks wrong if there's not that accent on there. Otherwise, I want to say finance. I know it's not, but I want to say finance. That's me. But which one is a user more likely to actually type, especially on a standard US English keyboard? So these are some classic scenarios that users expect a predictive text system to just handle naturally. It feels natural to a user for these sorts of tweaks to be made, but of course for computers, these sorts of things are anything but natural. You have to make sure to design for this. Languages with case sensitivity that applies in certain scenarios would like that to be maintained. If I capitalized my word, please keep it capitalized. If diacritics are difficult to type, we really like it and appreciate it when autocorrect can fill that in on our behalf and we don't have to think about it. I don't have to go hunting for that accent mark. I can just, oh, it'll fill it in. Cool. So, of course, how can we allow a language community to make sure that this behavior is maintained? For case sensitivity, we consider three main cases: lowercase, initial case, and unfortunately I hadn't fully read up on the documentation properly when designing this, so I called it title case, initial case. Hopefully we can find a good way to correct that at some point, but for now it's called initial. You can code this up in TypeScript to be able to follow standard casing patterns. We even provide a default version of this should you want your language to allow casing. Sinchan is an interesting example. It uses Latin script and it only uses uppercase aside from like a single letter. It does not use actual casing. So despite using Latin script, that is a uncased language. So we do need to maintain the ability for that to not be active, even when the script itself might suggest it should. Hopefully that's decently visible. If not, my apologies. And it's in the slides, so that's going to be fun to work with. So there's about 12 lines of code there. It's in a switch case statement that can go in and do transforms. A classic example is with Turkish. It follows all the standard casing rules, except for like a couple of things. You have dotted I and dotless I, which are two completely separate characters. And interestingly, unlike your standard Latin scenario, dotted I capitalizes to dotted capital I. And then you have dotless I capitalizes to uppercase dotless I. Rather than having dotted I go to dotless capital I, because we don't have that distinction in English or Spanish or French, but Turkish does. So we need to add a little override. So you can just do a small, actually simple regular expression focused on that one case, perform that correction directly, and then just do the defaults. We'll even pass your function a default implementation so you can only implement the overrides you need and rely on the defaults for the rest. Then, of course, it's also really useful in doing initial casing if you can just say, hey, use your own implementation to change the first character and to uppercase, and then keep everything else the same case as before. There are a few good non-spacing marks in Keyman that can serve as examples of things that you might consider diacritics if you were doing predictive text. There are these consonant shifters that apply above a consonant that always require an extra keystroke. There's also this shortener/val modifier, depending on which constant you apply it to, that also requires an extra keystroke. And you'll note in this particular layout, 2 of the 3 of them aren't even a base key. So it could be a bit of a pain for users to go hunt them down. They might prefer it if the autocorrect system automatically did that. So for that, we have something that is termed search term keying, which I've actually come to think of as a diacritic insensitivity. Like you have case sensitivity. When it comes to predictive text, you can think of there also being a diacritic sensitivity and insensitivity. Users often, when lazy, will be like, that diacritic doesn't matter. I don't need to type that. The system should just automatically know and map it to the same thing. How do we capture that language-specific knowledge into a way that then the model engine could also recognize, wait a second, users are going to think that these are the same. So I should suggest this version with these marks that they may have omitted. Now, of course, that's something that you can't just magically know about a language. That knowledge does have to be captured. So a little bit of code you can add. Again, apologies for those actually not even too far back from the sound of it. Sorry. But a couple of replacements to be like, hey, so here's some marks that the user typed, or that may be in the word list. We actually apply it on both ends. So users will tend to ignore this when lazy. So let's strip it out for the keyed version, for the version that's actually used for lookup operations. Then as a user types, let's also strip it out there too. If the stripped down version of both what is in our dictionary and what the user typed match, this is probably a good suggestion. Let's use it. Then, as far as case sensitivity is concerned, what was their initial case? Cool, let's apply that too. And so this function here is, again, about 12 or so lines of code. And this is for a custom implementation. For Latin-based scripts, we know those well enough to make some good default judgments about which diacritics we can strip off in a similar manner. But for non-Latin script, like Keyman is decidedly not, that needs to be manual. We can't know what's appropriate for every language. And so you can go in and have that be handled, and the system will then adjust. So between those two functions, where we've got that apply casing and the search term keying, that's a total of about 25 or so lines of TypeScript JavaScript code. It's enough so to where you could ask somebody who actually knows programming for an hour or two of time, ideally. If assuming, of course, you already have done the full analysis and know exactly what you need to strip and exactly how to handle casing. But that's even enough to where, 2 years, we've gotten 20, 24 or so models in our system. Somebody could even get in touch with us right now and ask, hey, how do I do this? That's a small enough range you can ask somebody for help and actually expect to receive an answer in a reasonable amount of time. JavaScript is a common language. So there are still a few technical barriers, but they're really low there. And so this lowers the bar as much as possible to where even minority languages should be able to actually get something in place. And I believe it has been noted by some that for just language revitalization and maintenance of a language, predictive text really helps with usability of a language. When you don't have to constantly fight the keyboard, hey, this suggestion thing can actually help me use my language more easily. It can give them a lot of value if we make this as accessible as possible. Now, of course, there's the natural question, will this perform as well as my iPhone's default English model? I think the answer is obvious. No, don't expect that. But if you have the choice between either no predictive text or some, which would you probably take? As long as it doesn't get in your way. having some good measure in is a great first step towards getting that language better support for technology in general. So I could take questions at this time, or I could actually demo a little bit of an aspect of the engine. I can show how it actually does adjust automatically based on what keyboard you have active. Well, actually, sure, let me pull that up real quick. So I set that up on another tab. Oops, no, there we go. So with our default keyboard that we distribute for English, this one's actually designed to handle a lot of Latin script languages. You'll note your standard QWERTY style layout here. Based on where you press on a key, you can have some pretty smart adjustments be made. Notice I clicked the very lower left corner of that O twice. It's very close to both the I and the K keys. So for a pretty likely fat finger, it's going to be like, hey, this is actually a pretty strong possibility. And like is actually enough more free, it's a more common word, enough so that it actually takes the top suggestion spot over what was actually typed, which is actually fairly reasonable for something that's that close of a fat finger. Now, if instead I click near the center, it doesn't win. Now, if I take a very different keyboard layout, the dreaded, infamous Dvorak. Well, dreaded by many, not necessarily by certain individuals in the room, I don't know. So actually, normally, L is nowhere near an R. Let me get a space in there real quick. Normally, E and A are nowhere near each other. I meant E and O. But even though Dvorak was definitely not involved in the design of this model, it was designed not considering any specific keyword whatsoever. Note how by clicking near the very left-hand side of the L, close to the R, which it's normally not anywhere near on US English. I click the right side of the O, near to the E on Dvorak, but very distinctly in a different place on US English. And then an A really became the most likely suggestion. We clicked very close to the R, a natural replacement. We clicked very close to the E, a natural replacement. And so no matter what keyboard is used, you can have all sorts of different layouts. Our predictive text engine will do fat fingering based on your layout at the time. The model could have been designed before this keyboard, some completely radical new layout, we'll still do fat fingering right for you. Now there's definitely a lot of runtime calculations behind the scenes. Using a word list and does allow us a fairly optimized data structure on that end. You have to be careful about the lookups and of course choosing the right paths to search down. There's a lot of thresholding, including time-based thresholding to make sure we don't just burn resources. But you can actually make something that's more generalized and that's not super tailored to a single language. And it actually feels like it performs pretty well, especially for not having access to smart data or part of speech tagging. It still feels remarkably reasonable. It's even been noticed by a colleague that you can even turn off, I believe, the fat fingering probability part, and it'll still feel remarkably smart about how it makes its suggestions. Or it might have been the other way where we disabled one aspect of their standard spell checking and just got the fat fingering. So there's still a lot of intelligence even without highly tuned language-specific knowledge. Just having the words, knowing the layout, and using them together really well in a generalized way can actually provide a remarkably good solution for languages that otherwise would not have anywhere near as good of an access to predictive text. So this could So we aim for this to be a good way to get a first solution out to a lot of languages that would love to have it. And at this time, I'm going to stop and take questions. Is it 5 minutes? Okay. Yes?
Does the keyboard do any learning from the user, saying that I keep typing a word that's not in the word list? Will the keyboard eventually figure out that that's something I like to type?
At this time, we do not have that functionality. As mentioned before, limited manpower, limited time. I actually have done a lot of study into machine learning. I would love to get set loose on that, but there's so many things that are buying up amounts of our time. Right now, admittedly, we're more focused on the LDML keyboard initiative and making sure to get that well supported, get an initial reference implementation. But I eagerly await the day I can turn my attention there. But not yet. But we do have plans on the roadmap. Eventually, fortunately, I don't even have a guarantee of what time that is.
British English versus American English. Do you need different models for that?
You could absolutely have different models for each one. If you specify, hey, I'm using EN-US versus EN-UK. Oh, so if you're using this as a EN-UK keyboard, here, let's look for an EN-UK model. So it's bound to the PCP47 tag. If your keyboard is, if you have that keyboard downloaded and registered for use with your UK English, we'll then look for an UK English model. And if we don't have one, we'll have to give up, or you could say, okay, I'll settle for EN-US and use a US model. But it's based on that tagging. Models can be registered for multiple regions, perhaps. So like you might be fine having UK, Canada, and Australian using the same model, since those regions are more closely tied in vocabulary than US English, although there definitely is some distinction in some of the more colorful aspects of each region's dialect. I didn't even think about that, but yes. Yes?
I tried building a predictive text model months ago for Nigerian pigeon.
Okay.
And there are two orthographies that are proposed, one that doesn't use many diacritics, one that does. And the people I was in contact with said, oh, that version without the diacritics is all wrong. At that time when I was doing with Keyman developer, it had me develop the model separate from the keyboard.
That is correct.
Is that still the case?
Yes, they're completely separate. So you could have entirely different groups manage the keyboard and model if needed.
Do people have to load those separately, or do I bundle them when I deliver a Nigerian pigeon?
So our applications that have predictive text enabled are designed so that when a user downloads that, if they download that from our distribution, it will automatically look and be like, oh, they've just downloaded this keyboard. What are the tagged languages that they installed for? Do we have a model for that? And behind the scenes, it will auto-install the other one. But they are separate files, but we just streamline that. But if a user is distributing that user to user on their own devices, that does have to be manually handled as two separate files.
I'll try it. Suppose that I'm a Keyman user, not a developer.
Yes.
Is there an avenue for me to supply a personal additional list of words that I want supported, similar to how you can in the Mac OS standard spell checker, if you type an unknown word, you can control click it and say add punishment. And then it ends up in a separate file underneath the hood that basically includes it.
We do not yet have that at this time, but I definitely look forward to us getting that in. I'd imagine that will beat actual machine learning, though depending on how our roadmap goes, it may fall at a somewhat similar time. I do believe that is an omission, to be sure. It's just, triaging good old software development issues. And it looks like that's time.
That's it, yeah.